Hello everyone. I hope you are doing well. And please be careful and stay away from this COVID-19 virus. This week we are continuing on the mechanical properties of materials again. And in today's lecture, we will be covering stress-strain testing of materials, how we perform such tests. And having learned what stress and what strain are last week, hopefully you will be able to follow today's lecture. But before we continue, let me turn myself on so that we can continue that way. As we have seen last week, mechanical properties are the properties that determine the response of engineering materials to applied forces. And we have seen last week some simple states of stress. Like we have seen that whenever we subject a rod to tension forces on each side, we will be seeing uniaxial tensile stresses in this member. Or for the same rod, if we are applying a uniaxial compression, then the state of stress is said to be uniaxial compression. Or sometimes we apply the rod what's called a torsion type of loading, and in that case we will be seeing a pure shear state of stress. Or sometimes if we apply a pressure inside this rod or chamber, let's say, we will be seeing a biaxial tensile type of stress. And the mechanical properties of structural materials are often determined through uniaxial loading of the material, either in compression or in tension. Therefore, whenever we are trying to learn the mechanical property of a material, we often subject that material to either uniaxial compression type of stresses or uniaxial tensile type of stresses. And the testing is performed in specially designed loading frames by measuring both the applied load and the deformation experienced when the material is subjected to those loads. Here you see a picture of what we call a universal testing machine. This is a classical type of universal testing machine that exists in our labs. If we were to schematically look what's in this machine, we have a movable crosshead, and at the top and at the bottom we have the restraining frame, and then this movable crosshead can go up and down, and most of the time we place specimens that we are subjecting to tensile tests at the top, and at the bottom we place for the materials that we want to apply compression. Of course, we can monitor the load and we can control the speed of this crosshead. Like if we are testing a concrete, for compression, that's what we test concrete most of the time, and we put that at the bottom space, and then as this cross frame moves down, there will be a reaction force at the bottom, and then we can determine therefore the compressive strength of concrete, for example. Or sometimes we want to test a rebar, a steel rebar in tension, then we place that at the top space, and then again we move the crosshead downwards, applying a tensile load to this rebar, and then a reaction force will be occurring at the top, and then we will be testing the uniaxial tensile strength of steel rebar. But nowadays we have modern versions of these universal testing machines. Again, this is a picture that I took from our lab. This is a machine that we have, a modern machine. But things are not that different than the classical ones. Again, we have a crosshead that's adjustable, and we adjust for the specimen height. It can go up and down. But the load is not applied through this crosshead. That's the difference. The load is applied by that piston that you cannot see right now. It's embedded into this frame. It's a hydraulic piston. So the hydraulic piston goes up and down, and depending on what type of a testing you want to perform, you place your material over here. And then this hydraulic piston is of course connected to a hydraulic pump, and that controls the movement of the piston up and down. Of course, since it's modern, it has a controller unit, and this is the controller unit of the system with a computer, of course. And the piston now can be controlled by this computer and the controller unit, and piston can be operated in either load controlled or displacement controlled modes. And you will be learning what those are in a little bit. Now, let's say that you want to test a steel rebar. You bring tension heads to this frame. You attach those to the top and bottom. And now there's another hydraulic pump that controls the pressure on the grips of the tension heads. So this rebar is attached to a grip system, and this grip somehow holds the rebar by applying again a hydraulic pressure. And steel rebar is directly attached to this tension heads. Now, this is another specimen, like a rubber specimen, and since the rubber specimen will be distracted by the tensile grips, we use a special fixture for holding that dog bone shaped rubber specimen. So there is a dog bone specimen in this fixture. Now, let's say you want to test a concrete specimen. You place a concrete specimen, and that will be subjected to compression. And you see over here the hydraulic piston that has gone up. And as the piston moves up, the concrete specimen will be compressed. And the reaction force or the load is recorded by this what's called the load cell. And sometimes we want to make some displacement measurements on the materials. And this displacement measurement on this setup is measured by using some LVDTs that are attached to a contact extensometer. The extensometer I'm talking about is these three rings, basically. And what's an LVDT? The LVDT, it's an electronical instrument called linear variable differential transformer. So we apply, or as this material deforms, some using the concepts of electricity, we can measure the displacement of this rebar through this LVDT. Sometimes we can use other instruments, like this is a non-contact video extensometer, and the displacements are measured now using this video recording instrument, I can basically say. And this is another test setup where we are testing concrete in bending, and now we have attached the bending fixtures both to the bottom and to the top of this loading frame. Now, let's look at the stress-strain testing in uniaxial tension. And most of the time, we do this type of testing to steel rebars for metals, basically. And here you see a steel rebar, and then the load is applied by these tension heads, as I said, and it's recorded by this load cell. And the displacement measurements in this case are recorded by this non-contact video extensometer. Then now we have two types of data now, the load data and the displacement data. So which one is used where? And of course we do continuously monitor the load and the displacement, so we have another parameter, time, for this case. Now if we are controlling the displacement, meaning we are moving the piston, or we are controlling how fast this piston goes up or down, this is called a displacement controlled testing, or we sometimes call strain controlled. So we are applying, or we are controlling the displacement, and we are measuring whatever force we get from this load cell. So again, if I were to repeat again, displacement is applied, so this is the control parameter, and the force is measured. This is the output. The other way of testing is what's called a load control testing scheme, and in this case we are controlling the force and we will be measuring the displacement. And as you can see, the force is increased linearly in this case, and corresponding displacements are determined for this rebar. So if I were to repeat again, the force is applied, so it's the control, and the displacement is measured. This is not controlled. So once the loads and deformations are determined, now we can make these stress strain calculations that we have learned last week, and the stresses are calculated from the load values. See, this is the load that we are applying to a cross-sectional area, so we can calculate the stress for each load increment by dividing the force to the cross-sectional area. Then we can also calculate the strains from the deformation values. If you remember again from last week, the longitudinal strain equals the displacement divided by the original length of that rebar. So using this equation, we can calculate the strain value for each time increment. Then what we will get is the load displacement data, like this one. And from this load displacement data, we can calculate the stress, as I just mentioned, and the strain, as I just mentioned. Now, from this load displacement data, now we can obtain the stress strain data of that steel rebar. There is something that I have to mention, that the descending portion of this stress strain diagram can only be obtained during a strain controlled testing scheme. The reason is simple, because during a load control scheme, the load is applied linearly, and we cannot apply a unloading scheme. That's fine. So in our next video, we will be talking about elastic and plastic deformation, and we will look into ideal materials.